This story is not about the stars visible on a clear night. It is about the invisible fabric that holds the universe together, and about the boundary beyond which our home, the Milky Way, loses all power over space. That boundary, somewhere out there in the darkness between us and our neighbors, does not run like a line on a map. It cannot be drawn. It can only be felt through the motion of runaway stars, through the cold of intergalactic gas, through the slow pull of something that has no name. What we are going to speak about does not fit into a single thought. We are used to thinking of the galaxy as something complete, a disk, spirals, hundreds of billions of stars. But behind that form stands something else, dark matter, of which there is more than anything else, filaments through which heated gas flows, voids where there is almost nothing, yet which occupy an enormous part of space. We have neighbors, Andromeda, the Triangulum Nebula, dozens of dwarfs. All of us together form the local group, and that group in turn is a tiny node in a much larger structure, whose name is Laniakea. And even Laniakea is not the limit. Somewhere ahead a massive region is pulling. It is called the Great Attractor, and our entire corner of the cosmos is slowly drifting in its direction. What is at stake here is not a plot, not a personal drama. What is at stake is a way of looking, the familiar one in which we are the center and the point of reference, and the other in which we are the tiniest node of a web slowly stretching towards something we will never reach. And you, where do you draw the boundary for yourself? Between ours and someone else's, between what we understand and what we merely mark with words. What matters more, to see with your own eyes or to know that it exists, even if the light from it will never reach us? Listen, this story is about that very boundary and about how far it really runs. The boundary beyond which the Milky Way loses power over space is not a line on a map, not a mark drawn by astronomers onto a chart. It is the place where stars begin to move, obeying no one, going where forces of a different order, of a different scale, are leading them. This question only looks simple at first glance. As soon as one tries to give it a strict scientific grounding, it becomes clear that the answer requires simultaneous accounting for dozens of parameters. The distribution of matter in space, the directions of motion of stellar streams, the behavior of intergalactic plasma, the role of dark matter, and finally, those regions where the attraction of our galaxy weakens so much that the conditions around it cease to depend on the internal dynamics of the spiral disk. Such a point on a cosmic scale can be called the outer limit of local gravitational dominance. The precise value of this limit cannot be expressed in a single formula. Existing estimates, however, agree that the distance at which the influence of the Milky Way becomes negligible may exceed several million light-years. Beyond that mark begins territory that no longer belongs to our galaxy, only to the combined action of other forces operating in the cosmos on different scales. The reality of these boundaries is testified to by observations of the motion of dwarf satellite galaxies, by analysis of the distribution of gas clouds in the galactic corona, and by the results of numerical modeling of the interaction between large structures. To view the Milky Way as a closed, isolated system is impossible. It constantly experiences the influence of other galaxies, gravitational flows, and background forces distributed over an enormous volume. Nevertheless, our stellar system possesses its own center of mass, its own ballistic characteristics, and an energy distribution of stars which together form what is usually called the local structure of attraction. It is that structure which determines which objects remain gravitationally bound to the galaxy and which are able to leave it forever and pass into the rarefied intergalactic space. If an object recedes from the Milky Way at a speed exceeding a certain critical threshold, its further trajectory will no longer obey the galactic mass. This is precisely what is observed in the case of the so-called intergalactic runaway stars, objects torn out of the central regions of the galaxy as a result of gravitational interaction with massive structures. Scientific papers describe cases when stars, having received a powerful impulse while passing near a supermassive black hole, were ejected beyond the galaxy and went off into rarefied space, where the density of matter approaches the lowest possible values. These stars are a kind of probe, by means of which scientists study the outer layers of the gravitational field of the Milky Way. Their motion testifies that beyond the corona of the galaxy, a complex system of interactions unfolds. Remnants of gas clouds, streams of dark matter, and slowly moving stellar objects create there an environment that is far from absolute emptiness. The density of matter in these regions is significantly lower than in any part of the spiral arms, and approaches the parameters of the true intergalactic medium. But it is precisely in these remote zones that one can detect processes which help us understand the origin and evolution of large cosmic structures. In such regions, the presence of faint streams of radiant energy is presumed, a consequence of the scattering of stellar remnants, of the accretion of gas onto small black holes, and of the interaction of cosmic ray particles with the rarefied environment. To register these processes directly is extremely difficult because of their negligible energy level, but their traces sometimes can be picked out from the data of telescopes recording X-ray and gamma radiation. The greater part of what holds the universe together is invisible. This is not a metaphor, it is a literal physical fact. Analyzing the speeds of intergalactic stars, scientists identify the parameters of the distribution of dark matter because only its gravitational influence can explain the observed trajectories. Observable matter is simply insufficient to produce the required attraction. This indicates that the external environment beyond the galaxy is not empty. It is filled with an invisible component that presumably makes up most of the mass of all large structures in the universe. This invisible component forms the scaffolding supporting entire galactic systems. Beyond the Milky Way, this scaffolding takes on a particular configuration. It connects our galaxy with neighboring systems, forming a giant web of interconnected nodes, each of which represents a local concentration of matter, held together by the gravitational potential of dark masses. As one moves away from the galaxy, the share of dark matter in the total gravitational interaction grows, since visible matter becomes ever more rarefied and rare. Models show that dark matter forms long filaments, stretching over hundreds of millions of light years. It is precisely along these filaments that ordinary matter settles, gradually collecting into dense structures, galaxies, and clusters. If one considers the distribution of gas in these outer regions, then even the most sensitive telescopes detect only thin structures, rarefied clouds of hydrogen, helium, and traces of heavier elements. These clouds can stretch over enormous distances and possess a complex morphology. Their shape is determined by local streams, the influence of magnetic fields, collisions with flows of high-energy particles, and by the traces of galactic collisions that long ago ended. A portion of these clouds is connected with the remnants of dwarf galaxies destroyed by the gravitational forces of the Milky Way. The material of such destroyed structures forms long filaments stretching over distances comparable to the diameter of our galaxy. These filaments testify that the space beyond the galactic disk is formed not chaotically, but under the influence of organized processes unfolding over billions of years. Ionized structures concentrated in the intergalactic medium can be detected through the analysis of the spectra of distant quasars. Light, passing through the intergalactic medium, is absorbed at certain wavelengths and leaves characteristic traces from which scientists reconstruct the composition and physical state of gas in different sections of space. It is precisely this method that allows information to be obtained about the structure of space on large scales, into regions where other instruments cannot reach. Our galaxy is not alone. It is part of a family, but this family has a boundary, and beyond it something fundamentally different begins. If one analyzes the distribution of galaxies in the immediate neighborhood of the Milky Way, it is found that our galaxy is only one of the nodes of a relatively dense group, which includes Andromeda, the Triangulum Nebula, and a great number of dwarf galaxies bound by a common gravitational field. This structure is known as the local group, and its extent is measured in many millions of light years. The space beyond its bounds becomes significantly less structured. It is precisely there that the region begins, where the influence of individual galaxies ceases to determine the parameters of the motion of objects, and the gravity of superscale structures comes to the foreground. These structures are formed by aggregations of galaxies, connected by long filaments of dark matter and separated by enormous voids. In some models, such voids represent regions with a density of matter so low that they are regarded as natural laboratories for the study of the fundamental laws of the interaction of matter and energy. Inside such voids, massive objects are practically absent, and the distribution of plasma particles tends toward uniformity. If one were to move an observer to the edge of one of these voids, an entirely different picture of the cosmos would open up before them. The familiar star fields are absent there, and instead of bright structures, one might see only the barely perceptible glow of residual radiation, uniformly stretched through space. It is presumed that precisely such conditions correspond to the earliest stages of the formation of cosmic structures, that time when primordial matter was only beginning to condense into the nodes of future galaxies. Even in seemingly empty intergalactic space, something is there, an invisible web that permeates the entire cosmos. This is not an image, but a physical reality. Beyond the galactic disk, space is not empty, although its density may seem close to zero values. The intergalactic medium represents a complex system in which rarefied clouds of ionized hydrogen, traces of helium, streams of high-energy particles, and structures formed by the gravity of enormous masses of dark matter are distributed. Distances between individual sections with measurable density of matter may exceed many millions of light years, and yet this is not nothing. It is a distinctive environment in which its own laws, its own processes, and its own timescales are at work. If an observer were to find themselves outside the galactic disk, they would not see a bright stellar plane. Instead, only a faint, distributed glow arising from the interaction of cosmic radiation with rarefied plasma. Such a distinctive state of the environment is explained by the fact that regular star formation is absent here. Gas is not compressed into dense clouds under the action of local gravitational collapses, but remains stretched under the influence of enormous flows of matter directed along the filaments of the cosmic web. The intergalactic medium is one of the key components of the large-scale structure of the universe. It links galaxies together, creating a kind of highway along which energy and matter flow from one region to another. This web is not homogeneous. Some sections possess a greater density of dark matter, which leads to the formation of nodes with clusters of galaxies, whereas between these nodes stretch enormous voids with an extremely low density of matter. Research shows that the distribution of gas in the intergalactic medium may reflect the history of processes that took place billions of years ago. The remnants of shock waves from powerful supernova explosions or from the activity of quasars can propagate over distances comparable to the scales of entire groups of galaxies, altering the temperature and structure of the surrounding space and forming complex formations capable of existing for an extraordinarily long time. One of the characteristic phenomena in this environment is the turbulence of intergalactic gas. Despite its extreme rarefaction, the gas exhibits complex motions caused by gravitational oscillations and energy flows. Turbulence on such scales interests astrophysicists above all, in that it is capable of influencing the processes of galaxy formation. In addition, in the intergalactic medium, there exist so-called cosmic filaments, structures of rarefied hot gas stretching over enormous distances and serving as channels along which matter moves between large clusters. These structures possess a complex geometry and may be connected with the activity of ancient quasars. The intergalactic medium may also contain traces of ancient collisions between large galaxies, in the form of faint streams of gas moving at great speeds. Such streams can be detected through the analysis of radiation arising from the collision of gas particles with high-energy photons. In the emptiest regions of the universe, processes occur that are inaccessible to terrestrial laboratories. This is not nothing. This is another state of matter. Cosmic voids may occupy a significant portion of the volume of the universe. Inside them, massive objects are absent that would distort space-time by their gravitational influence. The motion of objects in such regions is subject only to a weak background gravitational field. In the most rarefied areas of the intergalactic medium, unique physical conditions arise. The interaction of low-energy photons of background radiation with rarefied ions forms processes that are impossible to reproduce on Earth. These processes may play a key role in the evolution of cosmic structures, but their study requires extraordinarily high-sensitivity instruments. Theoretical calculations suggest that in some areas of the voids, conditions may arise favorable for the formation of unusual objects. For example, extremely compact concentrations of dark matter are capable of forming local curvatures of space-time, which for now cannot be directly registered. Such concentrations may alter the motion of individual particles without leaving any trace in the visible electromagnetic range. If one imagines a spacecraft sent into intergalactic space, it would encounter a whole series of peculiarities. First, the absence of dense matter would mean that navigation would have to rely exclusively on gravitational reference points, the arrangement of large galaxies. Second, the craft would find itself unprotected from cosmic radiation, which in these regions is not held back by magnetic fields. The intergalactic medium may also contain small concentrations of dust, remnants of destroyed stellar systems, moving along flows of matter. Their interaction with radiation produces faint signals that can be detected only with the most sensitive telescopes. In the intergalactic medium, the familiar reference points are absent. The speeds of particles here may be significantly higher than inside galaxies, and collisions occur so rarely that their statistical description requires special models. In a certain sense, the intergalactic medium is a natural laboratory for the study of the fundamental laws of physics. Here one can observe phenomena that are absent in more dense regions of the universe. Thus, the intergalactic medium is a significant part of the cosmic structure. Despite its rarefaction, it plays a role in the formation of large formations, influencing the motion of galaxies and the distribution of matter on scales exceeding the size of individual galactic systems. There is an invisible sphere. Crossing it, an object will never return to the galaxy. Scientists call it the surface of zero velocity. To understand the structure of the local group is impossible without an analysis of the mechanisms that determine the motion of objects at distances exceeding many millions of light years. These distances are too great for forces emanating from individual stellar systems to dominate over them. As a result, the structure of the local group is determined by the combined gravity of dark matter, the distribution of intergalactic gas, and historical processes that unfolded over billions of years. The Milky Way and Andromeda represent the two largest and most massive objects within this system. Their masses are great enough for the formation of extended dark halos, stretching over hundreds of thousands of light years. These halos approach each other or intersect, creating a common gravitational potential that holds dwarf galaxies in relatively stable orbits at great distances. If one considers the structure of the local group in a three-dimensional representation, it can be likened to an elongated system of nodes, between which are distributed dwarf galaxies, gas clouds, and dark matter components. The motion of these objects is subject to complex laws, determined not only by the attraction of the central galaxies, but also by the distribution of mass of the entire structure as a whole. It cannot be said that the Milky Way is the sole center of this system. The massive Andromeda exerts a comparable influence, and their interaction determines the motion of a significant portion of the objects within the local group. Determining the outer boundary of the local group is a task with no simple solution. This boundary cannot be expressed as a spherical surface with a single radius. Instead, there is a transitional region in which the gravitational influence of neighboring superclusters begins to affect the motion of objects, and the trajectories of individual galaxies cease to be determined exclusively by the attraction of the Milky Way and Andromeda. To describe this boundary, the concept of the surface of zero velocity is used. This is a region where the gravitational force emanating from the local group as a whole is balanced by the general acceleration of the expanding universe. Objects located inside this surface move toward the central galaxies or are held by their combined field. Objects located beyond its bounds are gradually drawn into the general expansion of space and move ever farther away with no return. According to estimates, the surface of zero velocity of the local group is located at a distance of many millions of light-years from the center of the system, considerably farther than one might suppose, relying only on the dimensions of the visible components. This is explained by the fact that most of the mass of the local group is concentrated in the form of dark matter, inaccessible to direct observation. It is precisely dark matter that forms the gravitational scaffolding uniting the Milky Way, Andromeda, and the numerous dwarf galaxies into a single connected system. Although its presence cannot be detected directly, modeling shows that the dark halos of the central galaxies are capable of holding a significant amount of matter at large distances. The structure of this scaffolding resembles a web, in which individual halos are connected by thin filaments of dark matter, a kind of corridor along which matter flows between different regions of the local group. Inside these filaments, the distribution of gas is uneven, and the temperature varies depending on the degree of influence of the surrounding galaxies. The study of these filaments allows a better understanding of the mechanisms that led to the formation of the local group in its present appearance. The motion of objects within the local group is subject to complex patterns. Dwarf galaxies located closer to the outer regions may experience the influence not only of the Milky Way, but also of other massive structures situated on the periphery. Some of them are captured by the gravity of Andromeda and move toward its center. Others remain in transitional zones where different forces temporarily balance each other. But this boundary is not forever. The local group itself is slowly and unstoppably changing. In an unimaginable number of billions of years, the Milky Way and Andromeda will merge. This is already predetermined. They are already moving toward each other, and according to numerical modeling, their collision will occur many billions of years from now. This means that the current structure of the local group will in the future be radically transformed. The two largest galaxies will unite, altering the entire dynamics of the system. But even now, processes exist that are continuously changing the appearance of this structure. Dwarf galaxies approaching the central massive bodies experience significant deformation under the action of tidal forces. These forces stretch them, destroy their internal structure, and form long streams of stars and gas. Such streams are observed around a number of systems orbiting the Milky Way, and they testify that the boundaries of the local group are not fixed. This is a dynamic system in which matter is constantly being redistributed under the influence of large, massive bodies. These processes may continue for countless millions of years, gradually altering the appearance of the whole structure. If an observer were to find themselves at a distance comparable to the outer boundary of the local group, they would see space in which the influence of the Milky Way becomes weak. The motion of galaxies here is determined no longer by local forces, but by general flows of matter set by the large-scale structure. This transition is a key element in understanding how superclusters of galaxies are formed. Superclusters represent gigantic structures within which numerous groups of galaxies are distributed, linked by filaments of dark matter forming the scaffolding of the universe. The local group is only one of such structures, entering into the composition of a larger formation. This connection is determined not only by distance, but also by the history of the evolution of matter. In the early stages of the formation of the universe, small fluctuations in density that arose in the first moments of the existence of spacetime led to some regions beginning to attract more matter. These regions became the centers of future superclusters. Our local group is only one tiny node in a much larger structure, and this structure is also moving somewhere, reaching for something more massive. Beyond the local group, forces of an entirely different scale come into action. The space beyond its outer regions is an environment where the influence of individual galaxies becomes insignificant, and the gravity of superscale structures comes to the foreground, possessing such a great total mass that their action is felt at distances exceeding many tens of millions of light years. In these zones, the trajectories of individual galaxies cease to follow one dominant center and begin to move in accordance with the distribution of masses over enormous distances. The motion of objects is caused not by local interactions, but by flows of matter formed by large structures, whose gravitational influence spreads over hundreds of millions of light years. A special role here is acquired by attractors, regions of space with a high concentration of mass, capable of attracting objects located at a distance of tens of millions of light years. One such attractor is the region known as the Great Attractor, a region with a powerful gravitational field toward which galaxies of our entire corner of the universe are moving. It is precisely the center of a huge structure that unites the local group with a multitude of other galactic clusters. This structure is called Laniakea. It represents an enormous region of the universe in which the motion of galaxies is subject to a common gravitational attraction. The local group is only one of the countless nodes of Laniakea. The transition from the local group to Laniakea is carried out gradually, without clearly outlined boundaries. One can speak only of zones where the gravitational influence of the local group diminishes, and the impact of external masses becomes decisive. Between these structures, there is no clear line. Rather, there exists a complex network of zones in which a gradual decrease of gravitational potential occurs. These zones are characterized by complex dynamics. The motion of galaxies within them is subject not to local forces, but to flows of matter formed by larger structures. The Great Attractor possesses such a mass that our entire corner of the universe slowly and steadily drifts toward it. We too. Laniakea represents an enormous region of the universe. The filaments of dark matter in its composition stretch over hundreds of millions of light years, connecting the nodes, massive clusters of galaxies. Galaxies within Laniakea move not arbitrarily, not chaotically, but along strictly defined directions, oriented toward the Great Attractor with its colossal gravitational field. The structure of Laniakea shows that the universe is organized in the form of a complex web, where galaxies move not by chance, but along particular directions set by the distribution of masses over enormous distances. Dark matter forms the basis of this structure, and ordinary matter is located inside the filaments that form its scaffolding. If one analyzes the distribution of galaxies in Laniakea, a significant unevenness is discovered. In some regions, the density of galaxies is noticeably higher. These are clusters and groups linked by filaments of dark matter. In other areas, the density is significantly lower. These are voids, regions with minimal gravitational influence, where massive galaxies are absent and the motion of objects is subject only to a weak background field. Within the voids, physical processes proceed differently than in denser regions. Such areas may contain rarefied plasma, remnants of ancient processes, and traces of interactions between flows of matter. Light from distant quasars passing through the voids contains practically no traces of absorption, which makes such regions difficult to observe, but no less important for understanding the large-scale structure. Some models suppose that voids may play the role of reservoirs, where the initial conditions of the early stages of the development of the universe are preserved. These conditions may include the distribution of primordial plasma, density fluctuations, and traces of processes that took place in the first moments after the emergence of spacetime. The application of the method of gravitational lensing has revealed that most of the mass of Laniakea and other superclusters is concentrated in dark matter. Ordinary visible matter constitutes only a small share of the total content. The method is based on the fact that mass curves the trajectory of light passing nearby. Observing the displacement of sources, scientists determine the parameters of the distribution of mass in a region even where it cannot be seen directly. This confirms the hypothesis that dark matter is the main component of the large-scale structure. If one considers the region of transition between the local group and Laniakea, it can be seen that the interaction between different flows of matter leads to turbulence and the formation of local condensations. These condensations are capable of serving as seeds for future galaxies or small clusters. Massive galaxies within Laniakea possess a powerful gravitational potential and are able to influence the motion of objects on large scales. Their masses are so great that they curve spacetime, creating effects registered by means of gravitational lensing methods. X-ray telescopes allow the mapping of the distribution of hot plasma filling the space between galaxies within superclusters. This plasma, heated to temperatures of many millions of degrees by powerful gravitational flows and the activity of massive objects, emits X-ray radiation, which is one of the key instruments for studying the structure of such formations. In the transitional zones between the local group and Laniakea, the traces of events that took place billions of years ago have been frozen. Space keeps a memory of processes that are long gone. The transition to Laniakea is accompanied by a change in the character of the distribution of gas. If inside the local group gas may be concentrated in separate clouds, then at the borders of the supercluster it is distributed differently. It turns out to be heated to temperatures exceeding many millions of degrees, under the action of powerful gravitational flows and colossal masses. This transition is also characterized by the formation of local condensations, whose formation depends on the distribution of dark matter and the peculiarities of local flows of gas. Remnants of shock waves generated by supernova explosions or by the activity of quasars are preserved in the form of rarefied structures stretching over enormous distances. They carry within them traces of events many billions of years old. It is precisely in these transitional zones that one can read the history of the universe, as in geological strata, only instead of stone here, it is rarefied hot gas, and instead of fossils, waves of dying radiation. This transition clearly shows that the local group is only a small part of an enormous system. The structure of the universe on superscale distances demonstrates patterns that cannot be seen in the study of one galaxy or even a whole group of galaxies. Understanding this connection is important for describing how the large-scale structures of the universe arise. Beyond Laniakea, the scales become so enormous that the human mind loses its usual supports for comparison. Beyond Laniakea, an enormous region including within itself millions of galaxies, the architecture of the universe begins to manifest itself, formed by filaments of matter, large nodes of massive clusters, and gigantic voids whose extent may exceed hundreds of millions of light-years. These structures form a single scaffolding on which all the visible and invisible matter of the cosmos rests. If one observes the distribution of galaxies on a three-dimensional map of the universe, it resembles a web of nodes and bridges. This web is not random. It reflects processes that took place in the early universe, when small fluctuations of density served as the source of differences in the distribution of matter, from which the large-scale formations gradually arose. These fluctuations served as the seeds of all the subsequent structure. From negligible inhomogeneities grew the whole web of galaxies, filaments, and voids that we see today. Beyond Laniakea, the filaments of dark matter become more pronounced. Distances between nodes here exceed many hundreds of millions of light-years. Some of these nodes represent enormous clusters of galaxies, each of which contains thousands of stellar systems. If one views them at large distances, they look like glowing patches among dark areas. At the borders of the voids, the density of dark matter slightly increases, which leads to the appearance of chains of galaxies located along these borders. In three-dimensional space, these chains resemble narrow bridges connecting large structures. They link the nodes in which clusters of galaxies are concentrated and ensure the movement of matter between different regions. Flows of gas and dark matter move along these bridges, forming a complex dynamic. On large distances, the motion of matter is determined by global flows directed toward massive structures, and these flows may cross the boundaries of superclusters, going off into other regions of the cosmic web. If one analyzes the distribution of galaxies beyond Laniakea, it can be noticed that some of them move along trajectories directed toward outer nodes. This testifies to the presence of powerful gravitational fields located outside the visible boundaries of our supercluster. Such fields are formed by neighboring superclusters with enormous total masses, capable of attracting matter from large volumes of cosmic space. Modeling shows that such structures are able to influence the motion of galaxies located far beyond their visible boundaries. The universe is not divided into isolated areas. It is a single system in which matter is constantly redistributed by global flows. Dark matter played a key role in the formation of this web. In the early stages of the development of the universe, it gathered into long, fibrous filaments, threads connecting large areas with high density. These filaments became the scaffolding around which ordinary matter began to concentrate. Gas, dust, and plasma accumulated along them, creating conditions for the appearance of galaxies and clusters. In the early stages of the universe, the distribution of density was relatively homogeneous, but small fluctuations gradually led to some areas beginning to attract more matter than others. These areas became the centers of future filaments, which grew over time, connecting large nodes with one another. Dark matter does not interact with ordinary matter through electromagnetic forces. That is precisely why it does not form dense clouds. Instead, it is able to create extended gravitational structures encompassing enormous spaces, inside which visible matter concentrates, forming galaxies and clusters. These processes unfolded over billions of years. Without dark matter, galaxies could not maintain their shape and could not hold together. This is confirmed by modeling, which shows that only the presence of invisible mass allows one to explain the dynamics of the motion of objects in large clusters. The intergalactic gas, moving along the filaments, is heated to high temperatures. Gravity causes its compression and heating. Observations show that such structures can stretch over hundreds of millions of light years. Stellar systems also move along these formations, although their motion is subject to more complex laws because of their significant own masses. But even it is ultimately determined by the global flows set by the distribution of dark matter. Galaxies located at the intersections of the filaments often possess special characteristics. They may contain more gas than galaxies inside the filaments, since the intersections are zones of concentration of matter, where gas is gathered in quantities sufficient for active star formation. Bright, active galaxies serve as indicators of such zones. Their radiance allows them to be detected at great distances, and the analysis of their spectra tells us how matter is distributed in this region. Dark energy, invisible, immeasurable directly, slowly tears apart what dark matter built over billions of years. Besides dark matter, a significant role in the formation of large structures may be played by dark energy, the driving force of the accelerating expansion of the universe. Its influence becomes noticeable on enormous scales, where gravitational forces cease to be dominant. Beyond Laniakea, the effect of dark energy gradually begins to exceed the local forces. Some regions expand faster than others, voids grow in size, and the filaments stretch under the influence of this expansion. Modern research shows that the structure of the cosmic web is not static. It changes continuously, though on timescales measured in billions of years. Filaments may stretch, nodes may shift, and voids may expand. These changes occur slowly and steadily, and it is precisely they that determine how galaxies and groups of galaxies will develop. Perhaps future generations of observers, if they exist, will see a picture in some ways similar to the present one, and in some ways strikingly different from it. That is precisely why the study of the structure beyond Laniakea is one of the important directions of modern astrophysics. It allows us to understand how matter is distributed in the universe and what forces determine its evolution on the greatest scales. There is a boundary beyond which we will never see anything, not because it is empty there, but because the light simply does not have time to reach us. The limits of the observable universe are determined not by distance as such, but by the time it took for light to reach us. An observer is able to see only what has managed to send its photon during the entire time of the existence of spacetime. Therefore, beyond the bounds of the observable sphere, there may exist structures that are inaccessible to registration by modern means, and they may stretch over distances exceeding many billions of light years beyond the line of the horizon, defined by the age of the cosmos. The observable part of the universe itself represents an enormous volume of space in which millions of superclusters are distributed. However, what is hidden beyond the limits of possible observation remains the subject exclusively of theoretical analysis. Models of the large-scale structure suppose that beyond the horizon may stretch the same filaments in voids that are observed in the accessible regions, formed by analogous laws and in analogous conditions. At the same time, the distribution of matter there may be either similar to the observable one or significantly differ from it. Regions are possible where the density of matter is higher or lower than in the observable sphere. There are hypotheses that beyond the horizon, there may be regions where matter is organized in configurations absent in the observable cosmos. For example, suggestions are made about possible superconglomerates whose sizes exceed the scales of any superclusters known to us. No less interesting is the question of the behavior of dark matter on scales exceeding the horizons of observation. It is not excluded that its distribution may form structures that cannot be seen because of the absence of signals. Dark matter does not emit electromagnetic radiation, therefore its behavior lends itself to analysis only through gravitational effects. And these effects become imperceptible if the sources are beyond the observable boundary. Dark energy, which determines the accelerating expansion of space, also exerts an influence on the structure of the cosmos. At large distances, its effect grows stronger. Some regions recede from each other faster than light is able to cover the distances separating them. Such regions vanish forever from the observable universe. The event horizon of expanding space creates for the observer an insurmountable barrier. If one considers the structure of the cosmic web near this horizon, the visible density of objects gradually decreases. But this does not necessarily mean a decrease of the real density. It may be only a consequence of the fact that light simply did not have enough time to cover the distance to the observer. There are theoretical models according to which the universe may be infinite. In this case, the structure of the cosmic web may continue without limits. However, infinity does not mean homogeneity. Some sections may have a density differing from the average. Regions are possible where the density of dark energy is higher than in the observable part. These regions may expand faster, forming new horizons. Several hypothetical scenarios can be distinguished, describing the structure beyond the observable universe. One of them supposes that the structure breaks down with the increase of distance. In this case, the cosmic web may have a finite extent, and beyond its bounds there may be an area with a practically zero density of matter. Another scenario admits the existence of massive objects so remote that even the light emitted by them in the early stages of their development has not yet reached the observer. Such objects could play the role of centers of attraction, around which superstructures form that exceed in size the superclusters known to us. Scientists nevertheless build models of what is hidden beyond this boundary, and in some of them reality turns out to be significantly stranger than everything we see. Among the speculative hypotheses connected with the structure beyond the horizon, A particular place is occupied by the notion of a multiply connected universe. If space can be bent in such a way that its sections are connected by bridges or tunnels, then some remote regions are able to exert an influence on one another despite enormous distances. In such models, the existence of paths is admitted, along which particles or rays can travel between distant regions, bypassing the usual spatial intervals. There are also hypotheses about supervoids, enormous regions with an extremely low density, capable of exerting an influence on the behavior of cosmic rays and the relic radiation. Supervoids may be connected with inhomogeneities that arose in the early stages of development. Some models admit the existence of regions where the concentration of energy has reached significant values as a consequence of the merger of massive structures that took place beyond the observable limits. If one considers the structure of the universe from the point of view of multidimensional models, space may have additional dimensions hidden from observation. The presence of such dimensions could explain some peculiarities of the distribution of matter. For example, large voids could be the consequence of the motion of matter in these additional dimensions. Some theoretical models also admit the possibility of the existence of pockets of space where the physical parameters differ from the customary ones, connected with fluctuations that arose in the primary moments of the existence of space-time. On scales exceeding the horizon of observation, processes may act that are connected with fluctuations of the vacuum. Some theories suppose that quantum effects on such scales may lead to the formation of microscopic regions with different physical characteristics. In theoretical cosmology, models are also considered that admit a change of the properties of dark matter depending on the scale, as well as variations of the density of dark energy in different parts of space, which could lead to the appearance of areas with accelerated expansion or with the slowing of processes, forming structures fundamentally not amenable to interpretation from the standpoint of observable physics. Accelerating expansion of space in the distant future may lead to some galaxies going forever beyond the bounds of the observable sphere. In such a case, the structure of the cosmic web will gradually become ever less accessible to the observer. Filaments will stretch under the action of accelerated expansion, voids will expand, and the connection between galactic structures will weaken. Some regions will find themselves so remote that contact with them will be lost forever. Nevertheless, even in such conditions, the structure on superscale distances will continue to develop. It will change by the same laws that govern it now, only without an observer capable of seeing it. Accelerated expansion will break the connection between galactic structures. The observable universe in the distant future will become significantly less saturated with galaxies, and this process will be determined by the global parameters of dark energy. The question of what lies beyond the observable universe may have many solutions. Different models describe different variants of the distribution of matter, energy, and dark matter beyond the horizon. Some of them allow us to imagine a structure exceeding in scale everything accessible to observation. Despite the absence of direct data, these models help us understand how the large-scale structure is formed and by what laws it continues to develop, there where we will never see it again. Please write in the comments how this story felt to you. It matters to me to understand whether it caught you. What do you think? The thought that our local group is slowly drifting toward the Great Attractor and will never reach it? Does it more likely calm or unsettle you? And also tell me, is it easier for you to watch horizontal footage or vertical for the phone?